Hi everyone, this is test 3 of the continuation of testing the floor's twist drive concept. And what I have made a change here, and basically it's the magnet configuration. I had modified, or I had made my own kind of design, which was those ring magnets in the previous tests. And what I've done now is I've gone to magnets in the same kind of geometry that Floor has been testing. And that's actually a kind of rectangular magnets. He's been using rectangular ceramic magnets, but I've put on some rectangular neodymium magnets here. And that's what we'll be testing now. So I want to give a complete view of the device. You can't see that, but there's a chart on the other side, and it's a larger chart now. On this chart here, that's been actually redone as well, and that's a 90 degrees movement from here to there. And these are 10 degrees increments at the longer line here, and these are 5 degrees increments here. So basically here we are taking 18 samples here on the activating arm and disactivating arm. And on this side here, that's a new chart as well. Now with these magnet size, or this magnet configuration, there's a lot more travel than with the ring magnets that I was using. But there's a small amount of torque. I had foot-pounds, and using these magnets you have a lot more travel, but you're only with those two neo-magnets there, I'm getting about 0.34, somewhere around 0.35 foot-pounds of torque in average throughout there. So I've got a bolt here attached to it, and that's about 160 grams, somewhere around there, 150 grams. And the device, once it's activated, it can lift that. And that's pretty close to about 0.34 foot-pounds of torque for it to be able to lift that. And what I'm going to do is I'm going to put the camera on a tripod, and you're going to see the whole action of the device. So obviously there's our bolt, and there is the magnet that's fixed there, and that magnet's just going to go straight in and out. And obviously this one is free to turn, and when that goes in, this magnet goes in closer to that one, it's going to give torque. It's going to want to twist. And I have this side here limited, so it's going to lock at one point, so if not, that bolt's just going to go crashing on the other side. I don't want that. And I've got it limited as well to stop down here. And what I'm going to do is I'm going to go there and lift that arm, which just pushes. This is just a crankshaft here, and it just pushes this to go in that direction there. And that's it. That's the whole device. It's that simple. So I'm going to do that now. So here I am slowly activating the device here, and as you see, this is the only thing that's moving forward. It's not twisting or anything, it's just going straight forward. Okay, and as you bring it forward, if you can get close enough, now you start to see the bolt is going up. And obviously here I'm not fully engaged, but when I fully engage it, it lifts the bolt and it hits the stopper that I put there. So now if I remove it back a little bit and drop back this lever here, the bolt drops back down. Just going to do that one more time, and hopefully you'll get a understanding of what is going on here. So as I lift it, the bolt gets lifted up. So that is the action of the device, and now I'm going to just show you the results, the test data that I obtained. So right here, this is still the original first test data that I had with my Neo ring magnets, and basically we have achieved an extra 0.44 foot-pounds. So nearly half a foot-pound extra from the work of activating and then disactivating, adding all that up, and you know, making the difference of travel, because this actually wasn't traveling as much, but we divided that by 2 and anything. Anyways, you know, it came up to about 37% extra from the total amount of average torque that we got there. So this is calculated somewhere around the same way. We've got 18 samples that are taken from here, so basically at every 5 degrees. And this is what I put in here. And so we have, now these are not foot-pounds, I had to use grams because it's such a feeble amount, and the scale here is more accurate on grams. So that's what we're going to be seeing here. So, you know, here you see first 5 degrees was 40 grams, and on, 55, 60, on and on. And then I put that in a calculator to get the average, and the average to activate it was 59 grams. And then this was to disengage it. So that was all the data there, and that exactly came to exactly 55 grams. So in total I had to put 114 grams of work in and out to achieve a full cycle. And on the torque arm, when I would go on the other side and then measure the torque, this is how it starts out. We have 185 grams, 165 grams, and you'll notice basically there's a point where we get to like a flat. Here we have a 60 grams here, and if you look at the number here, we're right at the middle here. We're at 18, because on this output I have more samples actually on the output side, because we're measuring 140 degrees of rotation. So we have 28 samples on 140 degrees rotation. So that's how it starts. It starts out, you know, with a lot of torque, and then as it gets to the center, meaning the magnet here starts out here, there's a lot of torque, but once it gets to the center here, that's where it has the less torque, and then it starts picking up more torque as it, and what that's done, that's attracted the other magnet once it gets here. So once it gets there, that's where it would stop. I have a stopper that would rest it at that point. So anyways, I think you understand the whole principle here. So basically we had 106 grams, okay, of average pull force by entering all that in the calculator. And now, because I have 140 degrees of travel, and here I have 90 degrees of travel, I had to multiply this data here by the difference. So there's a 1.5556 of extra travel distance to come up with a comparison to use that data there, which is 90 degrees worth. And so basically once we do that, we have a total amount of 165 grams of average pull force there of torque, and which comes up to exactly 0.36 foot-pounds of torque. And that's when now we add these two here, and which is 114 grams, the work that we've put in, which we deduct now from that 165. So we're left with 51 grams of extra force there, and which I took 165, and that is our overage, and it comes up, from what I can calculate, about 31% of extra pull force that's there. And on my first test with my ring magnets, I got about 37% of extra. So we were at 0.44 foot-pounds, and here we're at 51 grams, which is, you know, a small amount. It's very, very small. Once you convert 51 grams into foot-pounds, it's a very small amount. But obviously there seems to be an overage, and it's in the same range as using the rig magnets. So there seems to be a consistency, because whatever change I make, I kind of seem to stay in the same range, which is interesting to see. And but obviously you can get more torque, but it doesn't mean that you get more power out of it. But probably if you got more torque, you can do more work. It might be more efficient to turn a heavier flywheel or something like that. So that will conclude this test, and I hope this is useful. Bye now.